Hello and welcome to part 4 of this automotive manifold tutorial. So in the last video we finished generating our mesh and now we're ready to set up our simulation. First I'm going to switch context from the mesh context to the simulation context using the workflow menu at the bottom of the interface here. Then I will create a simulation via the pie. So using the plus sign, I create a new simulation, then via the drop down I designate the solver that I would like to use, which is the open solver in this case. And then lastly I need to add the domain that I've created earlier to simulation 1. Then once I click apply and close, I can see that simulation 1 is created in the tree. Now I can proceed with the inputs for my simulation. I will begin in the numerics tab with simulation 1 selected in the tree, and here I will adjust the number of grid levels that the multi-grid acceleration technique will use. This essentially designates how many times or by how many levels your initial mesh will be coarsened throughout the computation, well, coarsened and refined. And it's important not to set a value that is too high, because you may end up with a mesh that is too coarse to capture your domain, or a mesh that is of a very low quality. And so both of these things can cause divergence. So you need to make sure, if you're going to set a high number of grid levels, that your mesh is fine enough to be able to deal with that. Next we're going to proceed to the control tab and define the number of iterations. This is the number of iterations on the finest grid level after coarse grid initialization. Right. Here you can also define the convergence criterion at which, so this is essentially the density residual RMS value at which your simulation will converge, or will consider itself converged and stop further computations. Okay, next I'm going to select the domain in the tree and go to physics in the properties panel. We will be running a turbulent simulation, and we will be using a 2-equation RANS model, which is the K omega SST model. We are not using a wall function, so we are resolving the boundary layer, which is why we created a mesh with a first layer height equivalent to a y plus value of 1. This is a low speed flow simulation, so our Mach number is less than 0.3, which means it's incompressible, and we are using a density based solver, so that means that we need to use preconditioning, which is why I've enabled low speed flow. We need to adjust the characteristic velocity. This value needs to be as close as possible to the maximum expected velocity magnitude in the domain. And then we can proceed to defining our initial solution. So here we're going to set the velocity components. We're going to leave the pressure and temperature as default, and we're going to input our K and epsilon values. The K value is identical to the value that we're going to set for the inlet, so are the velocity components. The epsilon value is 10% of the epsilon value that we will be setting for the inlet. This is something that will help us with convergence in certain cases. Then we can move on to boundary conditions. So I'm going to expand domain 1 in the tree, and I will also expand the manifold assembly so that I can see my 3 boundaries. I will start with the inlet, and here I will select velocity components in the properties panel, And then I will proceed to define the velocity components as well as the turbulence quantities. Now the K and epsilon value here correspond to a turbulence intensity of 5%, which is typical for internal flows. So that is where these values come from. This will be an isothermal simulation, so we're not worried about the static temperature. Next is the walls. We will be using Navier-Stokes walls, which is the same thing as a no-slip boundary condition on the walls. Then for the outlet, we're going to assign a static pressure. This is just below 1 atmosphere. And then, last but not least, we're going to select simulation, again in the tree, and go to outputs. And here we can define all of the quantities that we would like to have in post-processing. So I'm going to enable static pressure here. Okay, then I will save my project, and I'm ready to run the simulation. So I will simply click Run Simulation in the tree, and you know that the simulation is running depending on the status messages that are displayed in the tree here. So now it's starting resources, but once it starts computing, you can actually monitor the residuals via the monitor through the pie here. You can select between residuals, physical quantities, or probes if you've defined any. And now all we have left to do is wait for our simulation to converge. I'll see you in the next video.